do ray tracing. It's with thin lens. And ray tracing is something I find actually very interesting. It's something you do in optics. I think is you can see, it makes sense. There's a little bit of background you got to pick up about it, some terminology. We'll get into that. But ray tracing is something, and in the lab I just assigned, you'll see mainly the parallel rays going in, seeing how it's formed. But you could also use that to do ray tracing to some extent. Ray tracing works. It's very useful in the industry, in the optics industry. Ray tracing is how you determine where images is formed, and much higher level versions of it. There's programs that do ray tracing. Oslo Code 5, some other ones, I don't know, I haven't looked into the new ones lately. But those programs are very expensive, they're very precise, and they're very useful. And you've got 20, 30, 40, 50, 100 lenses together in a line for optical systems to do everything from making computer images, making parts for computer chips, to creating images of systems, to using diffractives as lenses themselves. The old projection TVs and projectors like you see used here, they use an imaging systems and ray tracing for that. I actually had to design a projection system for the test I had to take to get a PhD, and that was part of the optics section. I designed that out pretty much out of my head for that project. That was pretty interesting. It was fun. Did well on it. So let's look at some ideas on ray tracing, and then we'll actually go over some examples, and I hope you find this interesting. So what we're going to do with ray tracing is, of course, it uses the ray model, not the wave model for it. We're going to deal with, for lenses, this is for lenses, there's converging and diverging lenses. Now these lenses work based on function. Let me get rid of this, that's redundant. With converging lenses, basically light is focused to a point. With diverging lenses, it diverges or spreads out. Light spread out and doesn't focus to a point. It's a diverging lens, it doesn't focus to a point. Now, that's how they work. I'm not showing how they're shaped. In general, though, a converging lens will look something like that. It can look, we call it a plano convex lens. This is be a regular biconvex lens on both sides. Plano convex. Plane on one side, convex on the other one. And you can actually put lenses together, but we're not getting into that. That's a little much. Now, with diverging lenses, they tend to look like, of course, this would be caves in, so biconcave. And of course, then you can have plano concave. Plano concave, it can look like that. And that's, of course, it flipped relative to the direction light's coming into it. Excuse me. I flip these around. This direction of light We're going to leave this as such. Now, what do converging lenses do? Let's look at converging lenses. Converging lenses are magnifying glass, what you normally consider a magnifying glass. All right? It takes light coming in, and this is light coming in parallel, just like you'd use in your little simulation. And it's going to focus it all to a point. Well, you can't even see that hardly, can you? See if I can get another green one. Focus it to a point. This distance from the lens to the point where all the light focus is known as the focal length. This here is known as the focal point. Learning vocabulary. Learning vocabulary today. Alright? That's what part of this class is for today. We're going to call this the lens plane. Basically, it's the center of that lens. When we do our models, we don't really take into account curvature here, unless we're looking physically at a lens. We'll represent a lens by just dotted lines like this, because that's functionally what it does for this model. These are known as parallel rays, but you know that if you looked at the simulation. These systems here, one thing I want to make sure I get across, these are known as thin lens. If it's a thin lens, we can represent it using this model. Thick lenses, you can't. And we'll get into that a little bit in the next lecture. Thick lenses, you got to take into account curvatures, and that's outside the scope of this class. We'll just barely introduce it to you a little bit. But these are known as thin lenses. So what you assume here for a thin lens, you assume all refraction, the bending of light, occurs at the lens plane. You assume it occurs at the plane of that lens. Right here, that center. Basically, it's the center line running down through it. Okay? Now, that's what a converging lens does. A diverging lens diverges, spreads the light out. We're going to draw it right here. We have a bunch of light coming in. Parallel rays again, parallel rays. These are parallel rays. And rather than focus to a point, actually, if you looked at it at each surface, it actually wants to spread the light out. Can't get that one good. There we go. And it spreads the light out. Now, if you look at it from this side, and have the eye here, this doesn't form in a place where the light rays go to a point, as we said, by definition. But if we're looking at this light, our eye would extend those lines back out like on a mirror, a plane mirror. And it doesn't know the light rays got bent. So, it would happen, not that I fuzzed it a little bit, just to, in here would be, that distance here is the focal length. See that? For a diverging lens. That would be the distance away. And one thing I haven't drawn in yet, normally through the middle of the lens, we'll put a line here. And I should have that focused on that. There we go. axis. The optical axis moves through the center. It's like a center line for this lens as we run through it. You like to try to place everything nice along the center, both in X and Y. We're making an assumption here, just like in a Y in the vertical direction centered. You'd also, for a real lens, want to center everything up in X as well, as far as, in and out of the board, you can say. This direction really, for parallel rays, wouldn't matter. And if you want to do the simulation, you can play around and have that point be a little off, and you can see how it squirrels that focal point around. Now, optical axis, lens plane, of course these, you also want these to be perpendicular. Why? Thin lens theory doesn't work if it's not perpendicular, okay? When you have real systems, real optical systems, you spend a lot of time aligning optics. That's what you call a lens, a mirror, or something that you've got there, a polarizer or something. One of the things you spend a lot of time and you learn to do in the very beginning of doing, you're basically setting up optic trains of optical elements, is figuring out the tips and techniques allowing you to align everything up. That is non-trivial. It takes a little while, but once you get it and see why, it makes lots of sense. You just bam, go through it and make it work. It takes a few minutes to make it happen though. And once it's set, you lock everything down and you dare your buddies to come in and move stuff, or you're going to get them. You come mess with their project. Because it would take hours sometimes to get everything good and lined up. Alright. Now, there's that one thing I do want to say. This is the focal length. We can put this distance on both sides. It doesn't matter. Remember principle of reversibility. Light can come in this way and focus here. If we do it the other way, light will come in and focus on the other side. So, if this is the distance here, we can measure that to focal length as well. We'll call that F. And same for here. We can put the focal length. We're going to do this to help us do our ray tracing. We're going to set things up like that. One thing I do want to say, what if we have a lens? This is just a hypothetical. And very center of it. What happens if light comes in like that? Through the very center. It's going to go through the top part of the lens here, the bottom part of the lens there. What's going to happen to that light? How much refraction will it happen? Will it get bent away? Or towards like this direction? Or will it get bent up that way? Towards the horizontal or towards that vertical there? Which one will it get diffracted? You at home are now virtually, because I can't pretend you're not here. I could, but possibly say something about my mental condition. You're virtually at home, writing your answer, wondering what I'm going to tell you. Why is he dragging us out? Why isn't he going to just tell us the answer and get this over with? Okay, have you waited sufficient? Have you made your estimations? Now, raise your hand if you said we've been this way towards the vertical there. Okay? Raise your other hand if you thought we'd been that way towards the horizontal. Okay? You're both wrong. As he would say, Bart Simpson, no. You're both wrong. Because is it bent at all? That's the right answer. Because the curvature here actually cancels out the curvature there. So what happens is, if it goes through the very center, nothing happens to the light going through that lens. If it goes to the very center, it can go through like this. It can go through like that. It can go through like this. For a thin lens, remember this is thin lens, if it goes through that center, no refraction. Because the curvature on one side actually cancels out the curvature on the other. We will use that when we do our ray tracing. Okay? If you follow along in the book, some of you hopefully are. I'm going to turn the page now. We're going to actually look at how images are formed. You got to remember all this, right? That was your intermission. Let's look at a lens. Converging lens. Focal length right here and here. We're putting it on both sides. We don't know the direction initially. We're just going to put it on both sides. There's the lens plane. And let's set up a object. There's Cameron, because he's kind of skinny. But he's a happy guy, because he likes studying optics. So that's how you look at things in space, right, Cameron? Or electromagnetic radiation. If you want to make X-ray lenses, Cameron, we can talk about that offline, because you can't do that in a class. Okay? UV, sun, but X-rays, stop that. Alright. Now we said earlier that for when an object is formed, you can think of light is emitted from that surface, from all points of that surface, okay? It all comes out. And you can see it comes out in all directions. Now, we know if we have this sort of system, it'll form an image, okay? So what we want to try to do is let's pick a point on this person that would be useful that tell you something about that image when it's formed. Now, we could pick the foot and start drawing a bunch of light rays coming out. But that would just kind of tell us where he's at over here. It wouldn't tell us how tall he is. How tall he is would tell us the magnification. Okay, Cameron, you got your foot back. So what we're going to do is, let's draw this light coming from his top of his head. And all these rays coming out. Now we can draw these rays going out in all directions. We could do here and here and here, and we could draw in bunches of rays. Honey bunches of oats. No, bunches of rays. But looks like Cameron had a bad hair day. But what we're going to do is, and we can trace each one, and each one would focus to a point over here. At the same point at the top of his head. And the book does a good example of all those rays. But I'm going to cut through that a little bit and only teach you there's three we need to use. They call them special rays in here. And the three special rays are you could do this with just two rays and get the same answer, but it's like the old saying, any two data points determines a line. It doesn't tell you what's going on. We're going to use three of them as a check. So these three should all focus to a point, and that way you know you just didn't just draw two of them and you got an answer. No, that's not going to tell you because you don't know if you're right or not. Use the third one as a check. All right? So we're going to look at three special rays. So the first ray, you want it, and we're going to do something very, very similar for mirrors. Okay? Very similar for mirrors. The first ray that's going to emanate from Cameron's, top of Cameron's head is, it's going to be into the lens, parallel to the optical axis. We go in parallel to the optical axis. Out of the lens through the focal point. And it's just like those parallel rays from before. And that's the light ray. Okay? That's one. Q. Or if you're French, deux, or in Quebec. We go into the lens. At the center. And what's going to happen? As you just know, it's not going to be refracted at all. You're starting to see what's going on a little bit. Through the lens, unrefracted. Unrefracted. And the third one is going to go through the focal point on this side. In through the focal point out. Now, how will it go out? Now, if it goes in through the focal point, we got to use principal reversibility. What's the only way for light to come in this way for it to go straight through the focal point? Well, it had to go in parallel. So it's going to have to go out. Whoops. We're not using black light. That would make us witches. So out. Parallel. Now notice, did they get a same point? No. I mean, I freehanded this and everything. These points were probably a little bit off a little bit. It's not going to be exact if you freehand. Now, if you use ray tracing software, simulation stuff, if you do it, to scale, you can get some really close agreement on these rays. So I don't know which one's which. I got to cross here, here, and here. I'm going to put it in the center of it. And then, let me write this down. So in through the focal point, out, parallel to the optical axis. And what I basically have here now, it's kind of bleeding over this. I've got giant man Cameron, regular man Cameron, and if we shrink him, we'd have Ant-Man Cameron, and we could shrink him if we wanted with this. Optically, of course, not physically. Alright? And he looks like he's frowning, but only it's really, what is a frown? It's just a smile turned upside down. So, he's really smiling because it's an image of him from over here. So this is the image, we say. Cameron is the object, we say. And what can we say about this image? This image is real. You can take a piece of paper and form an image or something, form this image on something, like a projector screen. It forms a real image. You can see it from that projector screen. It's inverted. He's upside down. It's also, we could say, enlarged. It's magnified. So, in the lens parallel to optical axis, out to the focal point, into the lens at the center, through the lens unrefracted, in through the focal point, that's basically switching those around, in through the focal point, out parallel to optical axis. And when we see this image, we want to ask 3 questions. This one is real inverted and magnified or enlarged. The questions for the image: real or virtual. Virtual, your eyes have to form that image like with a mirror. Inverted or upright. Inverted or upright. And enlarged or reduced. Or you could just say, okay, it looks like after my phone updated, it doesn't like doing videos longer than 25 or 26 minutes or so. So I did a diverging lens here, and basically what I've done is I've just appended this on to the previous movie for this section. So what I did a diverging lens. You can see here, I set it up at a focal length here and a focal length there. And I continued using the rules for special rays for ray diagrams. And I put a little person there. We're making that Amanda. Amanda doesn't like to get up in the morning, so for Amanda. Now, we have one coming straight in, as you see here. And it went out as if it came from the focal point here. It diverges. It has to spread out, so you have to keep that in mind. So it acts in that manner. We have one through the center. It goes to the center, that lens, right through that optical axis right here. That one keeps on going straight. It is not refracted. And then the third one, which is in through the focal point. So we can't go through this focal point, but we look at this one above it, the first one, and remember principle reversibility. We're going to basically flip it. So it's going to come in parallel from this side, out, so it goes through the head right there. Now, it will go out at an angle such that it came from the focal point. Now, I drew the arrows at the end because I know it's really coming, but from the top of Amanda's head there. But we use that principle reversibility. And then we look. No real image is formed. It's got to be virtual. The lights doesn't come together. So let's put our all-seeing eye of Sauron out here and see if we can see the light rays coming together back in this direction. And what heck darn does it look like they do? They all come together right there at the top of the image of Frito's head. The image of Frito's head. So that becomes our image position. Now, this will then be the image distance. Of course, that's our object distance. That is definitely upright. It's not inverted. And the magnification is definitely reduced. It's less than 1. Now, you'll see in the book it's got cut off. The only part I got cut off. You can find magnification by finding the height of the image over the height of the object. The same ratio applies for the length of the image over the length of the object. So SI over SO. Now, in the book, you're going to see this with a negative sign. If there's a negative in front of this, it's going to be inverted, because what you'll say is that this distance, when the object and the image for lenses are on the same side there, you're going to say that this image distance is negative. But the book will go into that Just know that calculate the magnification per se is just the image distance over the object distance. In this case, it's less than 1 because that's little over big, and little over big is a fraction less than 1. So that is thin lenses and ray tracing for diverging lenses.